Some things are more simple than others. And then the first example is this. You have a stream. Let's draw it as a, one of you said m dot. M dot that that is flowing, perhaps downhill, flowing from one place to another place at a distance L, which is known. And over here, the stream continues. And the stream, now, stream, if you don't know stream, you've seen the rain falling on the ground. It flows in the beginning as a circular sheet of water, but soon enough it develops fingers or rivulets and so on. So those are streams. Even your the jet of air from your mouth is actually a stream of air through air. Everything is a flow with configuration. And the question is about the configuration here. Under the constraint that you, the thinker, you have a, let's call it a finite amount of ink with which to make the drawing, or if the page is of limited size, meaning you are once again a mortal. And we account for that statement of humility by saying that the space through which, or the space occupied by this flowing fluid is fixed. So the flow volume is fixed. I call the flow volume VOL, fixed or known, or something that I hang on to in order to be able to make a drawing. Known. And this is the beginning, you see. In the beginning, I have nothing. I have a page with infinite freedom. More than once I was asked, how do you measure freedom? I gave you one answer the other day, Raj. Well, you count the number of degrees of freedom. And yes, this volume that's supposed to be fixed, it could be, never mind, use your imagination, shapes of volumes. That volume could have any shape. I'll draw one that is a kind of weird. The weirder, the better at this stage. Here's a volume through which this fluid is flowing. Let me and so on. You get the idea that there is bifurcating, there is confluence. You can imagine any drawing of this kind. And all of this is the volume. And the question is, since you have infinite freedom to change the drawing, how should you change it in your mind so that the access from left to right is easier and easier? Well, you make several moves because you're not born yesterday. In fact, I will teach something that goes by the fancy name these days as economies of scale. This will be a special lesson called economies of scale. Which appears as a chapter in the book called Freedom and Evolution. We'll get to that soon enough. Economies of scale is the nothing new here, the that a stream perhaps this stream, m dot, that flows through two identical tubes, both of length L, flows a lot more easily through a single tube that has the same flow volume as the first two together. So the easier way to flow is through one. This is the first intuitive idea. Farmers in the American West know this. You want to bring meltwater from the Rockies, you don't build little channels in parallel. You build one ditch, they call it, and the ditch brings the water from the mountain to the plain. And it's only on the plain that the ramifications are implemented. So that's economies of scale, which means, with regard to this particular drawing, that meaning without having to argue with anyone, the better way to flow along that distance between those 2 points is through a single duct. And as the distance L fixed, and this is the volume V also fixed. But you look at these contortions, they're up to you. This drawing is full of degrees of freedom. You can bend that hose many ways. Here's where you compare infinite degrees of freedom with infinite degrees of freedom. In mathematics, some people talk about an infinity that's bigger than this infinity. Yeah, never mind them. Never mind them. Infinite means invisible or intangible or so far removed that you can't even imagine how big that number is. It's beyond my imagination, you see. You know what that means. That means it's impossible because my imagination is infinite. You see. Okay. You're not shocked, but you should be. So, out of this infinity, which one is the easiest way to flow? The straight tube, okay? This is the first aha, meaning the first reason to get up on a horse and ride home to declare victory, except that this drawing also has an infinite number of degrees of freedom. And that infinite number of degrees of freedom refers to the cross-sectional shapes. I drew the thing as a round tube because that's the easiest way to make a drawing. But it could be a cross-section that looks like a kidney, or some other cross-section that looks like somebody's, never mind. Or you get the idea, okay? This is a family of shapes. Each loop like this possesses, meaning to go from one to the other is to speak of an infinite number of degrees of freedom. You see, we're zeroing in on the domain in which these degrees of freedom become recognizable. And yes, of a relatively smaller and smaller number. But again, intuitively, before we get into the math, the cross-section that offers greater access the cross-section that's not round, but the cross-section that offers greater access is the one that looks roundish. And the roundish cross-sections that are not round are the regular polygons, such as a hexagon, and so on, or square. Get it? So you arrive at regular polygons. This too is a family with an infinite number of degrees of freedom. But that number now is recognized as the number of sides of the polygon. 6 here, 4 here. There would be 3 for the equilateral triangle, and of course many more going to the left. And that is the beginning of the mathematical treatment of the problem of identifying the flow architecture with greater access. And this is about the duct, meaning any duct, with let's draw a triangle here, length L, and regular polygon for the shape. Just a second. Here's the M dot. Yeah?
In this case, is access minimizing flow resistance, or like
well yes, that's the reason why I did not erase the drawing on the left side. I avoid the word resistance because it's thrown around by everybody. I mentioned the French resistance during the Second World War, and the human body being resistant to a virus. Resistance is a word that has its own meaning. It's one reason I speak of access. And access, when it comes to flowing through a duct, is about how much power you spend, meaning into a pump or into a compressor to push this M dot through. That power is proportional to the product of M dot and delta P. So when the mass flow rate is known, then Mr. Falbaum, the answer boils down to access means a lower and lower pressure drop required. But the reason why I kept this drawing was to inspire you to question me, because you see this kind of drawing on the wet beach, you know, right after the rain. There are these rivulets, they form naturally, and from time to time, they look braided. And they're natural. Yeah, why? Why do they look braided when in fact it's easier to flow from left to right this way, along a single channel? I'm asking you, come up with the answer, because your answer would then contradict me. And after you contradict me, I will warm myself from under your grasp. Yes. Who's you, Rose? You go first.
I would say the imperfection on the ground.
Wait. There's nothing more perfect than the wet sand of the beach, you know, because it is constantly shaved perfectly flat by the waves.
But it does seem like it's the.
Well, it's inclined, yes, yeah. That's why the water flows downhill. But the beach is one of the most perfect canvases on which people in love write the declarations. What, you don't know that? I recommend it. Okay. You.
Say the materials that the water has to flow through. So if it hits a seashell, the water is going to go around.
I just told you it's perfectly flat.
Well, but within all of.
Don't. It's perfectly flat. I can show you pictures. Any other?
The incoming water probably not totally laminar, so if the turbulence causes
No, it's laminar, believe me, because it's laminar. You can actually look at it. It's a perfect sheet of a uniform thickness that arrives, actually, it arrives from higher up from the cliff or whatever it is, where this water is accumulated, and then it spills on the beach. And it shows some of that. You don't know.
because it's trying to spread out into the ocean, which is much wider.
Yeah. You're getting to it. It's not the ocean. Let me. So downhill is this way. Let me erase this. And now you get the idea, meaning you discover something that most people don't realize. When the river arrives from the plain into this so-called wet sand surface, also known as silt, it sinks into it. It sinks. The water that arrives as rainwater sinks downward. Most of it does not reach the so-called ocean. And in other words, the tendency, yes, is to flow more and more easily from point to area and to make a delta. Now, I grew up in a delta, the Danube Delta. 70% of the water of the Danube sinks downward before reaching the Black Sea. And then after sinking downward, it flows horizontally as a sheet of water underground into the shelf of the sea. But this is the invisible flow that requires it to be recognized. Requires the kind of questioning that with which I was challenging you. Get it? And so the tendency called braiding is the tendency that gives birth to delta or to deltas. The opposite is this, meaning the coming of these branches together, is after the sinking, is the economies of scale that kicks in and brings the surviving stream together again to evacuate or to leave the area. So that's what happens in places where, never mind. So that's the answer to my own question. Yes?
Why would the sinking water, why did that cause it to spread out laterally?
Oh, on the beach?
The braid, yeah.
On the beach, I recommend you go right on the wet sand the way I recommended. On the beach, the higher, here's the profile drawing. Here's the beach. Here's the ocean, and here's of course the cliff with the palm tree. This sand is flat, it's inclined, but the uppermost portion is the driest. Meaning the spacings between the grains of sand are open. And that's why this process of vertical sinking is immediate and most intense when the water arrives. The water is mindless but not stupid. Okay, it chooses the easiest or first available path forward, and in this case, it is downward. And it is downward by conquering area, from which this drawing is born. If you guys don't ask questions, then the whole lesson is for.
all right. Thank you too.
Yeah. I was going to call you Nefertiti, but it sounds like that. Okay, fine. What's your question?
Why
next?
don't they just continue increasing indefinitely?
Oh, because because downhill, the pores are saturated with water, and this okay, and then the choice of so-called sheet of rainwater is to flow downward, and in that direction, it discovers economies of scale, which is that it's easier to flow on the surface as one channel. So flowing downward, access means a greater area, therefore delta behavior. Later, where the substrate is saturated, the easiest way out is to flow as one river.
Also,
It's counterintuitive, but that's the fun part of it.
wouldn't increasing the area decrease the pressure? Would it mean it goes
Everything is at atmospheric pressure. Pressure in a downhill flow is not an issue. If you're curious about this, write your term paper about it, and I will try not to interfere until the very, very end. But this, by the way, this is how your graduates of earlier versions of this course came up with their own ideas for their term papers, is by questioning. And those of you who are quiet from the back, strike a deal with the ones who are presently in front. You may have to pay them money so that you come sit in front and they go to the back, and then you learn to be like them. All right, next. It's funny. Here's one more lecture that will have to end next time. The next part of the story has to do with flow through a straight duct of known length, known flow volume, but unknown number of sides to the regular polygonal shape. So that is the next step. The way to express quantitatively access is by reporting to the skeptic the pressure drop that's required. This is one of the first formulas I put on the blackboard during the review phase of this course. It is so pressure drop is equal to a factor called friction factor for L over the hydraulic diameter of the cross section, and then 1/2 of rho u squared. This is a group at the end. A group at the end, which was invented, has nothing to do with nature. This group at the end has the units of pressure. Those units are Newton per meter squared, which are the units of the left-hand side. This is necessary because the friction factor is dimensionless. As is this ratio of L over D. Okay? Other definitions that I put on the blackboard earlier in the course are for the first the hydraulic diameter, which is 4A divided by the wetted perimeter. In other words, here's the cross section. Let's think about, once again, maybe a hexagon. This is a perimeter, an area, and that's hydraulic diameter. Capital U is the speed of the stream averaged over the cross section, and that means the mass flow rate divided by rho times A. And finally, friction factor. If you still have your fluid dynamics textbook, this is a time for you to to remember your professor by flipping through the textbook that that person used. But this is actually proportional, it's dimensionless, but proportional to the skin friction encountered by the stream as it wets the surfaces. So there is a tau and another tau and another tau everywhere. But expressed in dimensionless form, the friction factor is appears as a constant here, divided by the Reynolds number based on hydraulic diameter. All these formulas are review. You must have run into them. If you don't have them, they're in the textbook, the one with the problems at the end. The Reynolds number based on hydraulic diameter is U dH divided by nu. Nu is the kinematic viscosity, which is dynamic viscosity divided by rho. I'm putting these definitions on the blackboard today once and for all. But they are necessary because, after all, time is limited and we have lots of ideas to explore. And the constant is a dimensionless, just a second, dimensionless number that depends on the shape of the cross section. Yes, what's your
Saying 5 minutes left in
Huh?
class. There's 5 minutes left in class.
louder?
5 minutes left in class.
Oh, was that it? Oh, all right. And this constant is most famous, meaning it's known for the round tube. For the round tube, by the way, this constant these days has the name of Poiseuille constant. And the Poiseuille constant is 16 for a round cross section. The another half famous constant is 24 for a cross section that's shaped as a slit, meaning much wider than thick or thin, a slit. And then there's it varies from something like 13 to numbers of this order of magnitude. But it is obviously a constant of order 10. Speaking of orders of magnitude. Why Poiseuille? Who was he? This is like that famous question, where is he from? Poiseuille, yeah. Well, this one happened to have, he was French, okay? He's the one, but he was really an amateur. He was a medical doctor. He was not a physicist. Back then, there were no physicists. They were just curious people, you know, amateurs or polymaths. And he's the one who figured out that blood, because he was a medical doctor, flows with a parabolic velocity profile through the capillary, in this case, tube called capillary vessel. Poiseuille, medical doctor. And that's how this flow acquired the name of Poiseuille flow. Not long after that, when what's the word? The floodlights of scientific fame migrated eastward from France to Germany, scientists discovered that a German, imagine, a German had published the same result a little bit earlier, a few months earlier. This man's name is Hagen. Hagen. There you go. Hagen was just like Poiseuille, a medical doctor, a free spirit, not an expert. And so people who love history they call this flow Hagen-Poiseuille flow. And then very, very recently, this is after I stopped being a student, somehow the fluid dynamics community decided to, because fluid dynamics is full of German names like Prandtl and others, to commemorate the contributions of this early French pioneer. So that's why the name for this constant is Poiseuille.